Have you ever looked at a drop of black ink and wondered how chemists can possibly figure out all the different colors mixed inside? Well, they use this incredibly powerful technique called chromatography. The name actually comes from the Greek word chroma, which means color, because it was first used to separate all the colorful pigments in plants. Let's dive in and see how it makes the invisible visible. So what's chromatography really for? You can think of it as a chemist's ultimate 3-in-1 tool. First off, it's a master sorter. It takes a completely jumbled up mixture and neatly separates every single component. Second, it's a purifier. It lets scientists isolate and grab just the one specific compound they need, leaving everything else behind. And third, it's a quality check, confirming if a substance is 100% pure, which, as you can imagine, is absolutely critical in fields like medicine. So here's our game plan. We're going to start with the one core principle that makes this whole thing work. Then we'll explore the two main strategies that chemists use, something called adsorption and another called partition. And to wrap it all up, we'll lay everything out in a simple comparison chart so you can see exactly how they all stack up. To really understand any kind of chromatography, you only need to get one central idea. It's all about a universal tug of war, a constant push and pull. This image right here perfectly nails the concept. Just imagine a race. The racetrack itself is what we call the stationary phase. Let's call it the anchor, because its job is to hold the racers back. Now, the mobile phase is like a gust of wind or a current of water pushing everything along. We'll call it the driver. The magic of separation happens because some racers, or chemical compounds, have a really strong grip on the anchor, so they move slowly. Others have a weak grip, and they get swept forward easily by the driver. It's this simple difference in speed that separates the entire mixture. So, this simple idea of a race gives us two main strategies. The first branch is adsorption, and it's all about stickiness, how strongly different components literally cling to a solid surface. The second is partition, which is more of a chemical balancing act between two different liquids. Let's dive into adsorption first. All right, welcome to branch 1, adsorption. The keyword to remember here is adsorb, which pretty much just means to stick to a surface. And here is that stickiness in action. The stationary phase is like a microscopic obstacle course made of some porous solid. As the mobile phase washes over it, the components in our mixture have to navigate it. You can see the magenta particles here have a high affinity for the obstacles. They're grabbing on tight, moving really slowly. Meanwhile, the orange particles have a low affinity. They just breeze right past and get swept forward. It's that simple difference in interaction that sorts the whole thing out. Okay, so our first real-world example of adsorption is column chromatography. And honestly, it's exactly what it sounds like. You've got a vertical glass column, and it's packed with that solid, sticky material we just talked about. Let's do a quick tour of the setup. At the very top, we pour in our mobile phase, the solvent. Now, in this context, chemists have a fancy word for it, the eluent. It's just the liquid that's going to carry our mixture through the column. Below that, we add our mixture. The column itself is packed tight with the solid, stationary phase. And way down at the bottom, there's a little plug of glass wool that acts like a filter, and the stopcock, which is basically a valve that gives us precise control over how fast everything flows. And here you can see the process as it happens. We start with initiation. The mixture is just a single band at the top. Then, as the solvent drips through, we get to resolution. Look at that. You can see the bands literally resolving into separate, distinct colors. Finally, we have retention. The stickiest components are retained or held back at the top, while the less sticky ones have already been washed much further down the column. Now, a second really common absorption method is thin layer chromatography, or TLC for short. The principle is exactly the same, separation by sticking, but instead of a big packed column, the stationary phase is a super thin layer of silica or alumina that's coated onto a small glass or plastic plate. The setup for this is actually pretty clever. You put a tiny spot of your mixture on a baseline drawn near the bottom of the plate. Then, you stand the plate up in a sealed jar that has just a little bit of solvent at the bottom. The sealed jar is key, by the way. What happens next is the solvent defies gravity and climbs up the plate. It's a process called capillary action, the exact same force that lets a paper towel soak up a spill. And as that solvent climbs, it separates the mixture. So once the solvent has crawled up the plate and it's all dry, how do we actually analyze the result? How do we get data from this? Well, we use a value called the retardation factor, or RF. It's a really simple ratio. You just take the distance your separated spot traveled from the baseline, we'll call that X, and you divide it by the total distance the solvent traveled, which we'll call Y.
Okay, so there's a formula. But what does it actually tell us? What's the point? Well, that number is like a unique fingerprint for a compound, but only under very specific conditions.
Let's make this super concrete with an example. Imagine the solvent, our Y value, travels 10 centimeters up the plate. And our colored spot, that's X, only makes it 3 centimeters. So the RF value is just 3 divided by 10, which is 0.3. The key thing to realize here is that since the spot can never ever outrun the solvent, the RF value will always be a number between 0 and 1. And the lower that number, the stickier that compound is. But what if your compounds are invisible? I mean, not everything in chemistry is brightly colored. Well, chemists have a couple of really cool tricks up their sleeves. The first one is basically like using a black light. They shine a UV lamp on the plate, and a lot of compounds will actually fluoresce, glowing brightly so you can see them. The other method involves an iodine chamber. You just place the plate in a jar with some iodine crystals, and the vapor sticks to the organic spots, revealing them as brownish smudges. All right, let's move on to our second branch. This is not about sticking to a solid anymore. We're talking about a completely different mechanism called partition.
This slide really gets to the core of the difference. Adsorption, as we saw, is about sticking to a solid. Partition is totally different. It's all about dissolving. Think about a salad dressing with oil and vinegar. The components of your mixture are constantly having to decide which liquid they'd rather be dissolved in, the stationary liquid or the mobile liquid. They are continuously partitioning, or dividing themselves between the two. The separation happens simply because some components prefer to hang out in the stationary liquid, while others would rather go with the flow of the mobile liquid.
The classic example of this is paper chromatography. Now, the setup looks a whole lot like TLC, but the science is totally different. Here's the mind-blowing part. The paper itself isn't the stationary phase. The true stationary phase is the microscopic water molecules that are naturally trapped inside the cellulose fibers of the paper. That's our stationary liquid. The mobile liquid is the solvent that climbs up the paper by capillary action, and the separation happens based on how the mixture's components partition themselves between that moving solvent and the trapped water. Okay, we've covered a lot of ground. We've seen 2 fundamental principles and 3 different techniques. Let's synthesize all of this information into one single, clear comparison. This table right here pulls it all together perfectly. Let's just walk through it. Column and TLC are both based on adsorption. They both use a solid stationary phase. The main difference between them is how the mobile phase moves. Gravity pulls it down in a column, while capillary action pulls it up in TLC. Paper chromatography is the odd one out. Its guiding principle is partition, because its stationary phase is a liquid, all that water trapped in the paper fibers. And, just like TLC, it relies on that upward capillary action. Finally, just look at the output. Columns give you separated liquids that you can actually collect, while the other 2 give you a finished 2D image, a picture of your separation. So if you're gonna remember just a few things, make it these. First, all chromatography works because different components move at different speeds through a system with a stationary phase and a mobile phase. Second, the 2 main engines driving this separation are adsorption, which is basically about sticking, and partition, which is all about dissolving. And finally, for TLC, that retardation factor, RF equals X over Y, is the simple but really powerful formula we use to actually put a number on the separation we see. It's an amazing technique that turns invisible complexity into visible clarity. So I'll leave you with a final question. Now that you know the basic principles, what invisible mixtures in your own world, from the ink in your pen to the spices in your kitchen, would you be curious to separate?